Welcome to this coding problem walkthrough. Today, we'll be tackling group-shifted strings, a fascinating problem that challenges your string manipulation and pattern recognition skills. Stick around as we explore the problem and break it down step by step. In this problem, you are given a list of strings, where each string consists of lowercase English letters. The goal is to group these strings based on their shifting patterns. What does this mean? Two strings belong to the same group if you can shift each character of one string to match the other. Shifting a character means moving it forward in the alphabet, with wrapping at the end so Z shifts to A and A shifts to B. For example, the string ABC can be shifted to BCD, and BCD can be shifted to CDE. Your task is to group all strings that belong to the same shifting pattern and return these groups as a list of lists. Each group of strings must be sorted lexicographically, and the groups themselves should also be ordered by their first string in lexicographical order. The input list can contain up to 10,000 strings, each with a length of up to 50 characters. The output of the problem is a list of lists, where each sublist contains strings that belong to the same shifting group. Within each group, the strings are sorted lexicographically, and the groups themselves are also sorted by their first string. Let's look at an example. Suppose the input list is ABC, BCD, ASF, XYZ, AZ, B, Z. The output would be Z, ABC, BCD, XYZ, ASF, AZ, B. Here, ABC, BCD, and XYZ form one group because their shifting pattern aligns. Shifting ABC gives BCD, and shifting BCD gives XYZ. Similarly, A and Z form a group because shifting Z forward wraps it back to A. The strings AZ and BA also form a group for the same reason. Lastly, ASF forms its own group because no other string matches it after any shifting. To further clarify, let's break down the explanation of the example. In the group ABC, BCD, XYZ, notice that shifting each character of ABC by 1 results in BCD, and shifting BCD by 1 results in XYZ. This demonstrates that all three strings share the same shifting pattern. In the group Z, shifting Z by 1 wraps it back to A, which means these two strings belong together. The group AZ-BA works similarly. Shifting AZ by 1 gives BA, and shifting BA by 1 wraps it back to AZ. Finally, ASF is in its own group because no amount of shifting can produce any other string from the input. Another example involves the input AA, AAA, AAA, where each string is in its own group. This is because no shifting operation can make two different strings identical. Now, consider an additional example with the input ABC, DEF, GHI, JKL. Here, all the strings belong to the same group because they share the same shifting pattern. For instance, shifting ABC by a fixed offset gives DEF, and shifting DEF gives GHI, and so on. Since all these strings align with the same shifting logic, they are grouped together. This demonstrates that a single shifting pattern can include multiple strings, even if the strings appear different at first glance. The grouping is entirely determined by whether the shifting operation can make one string match another. Finally, let's discuss the constraints and edge cases. The input list can contain up to 10,000 strings, and each string can have a maximum length of 50 characters. This means your solution must be efficient to handle large input sizes. As for edge cases, consider a single string in the input. This will simply form a group on its own. For example, if the input is ABC, the output is ABC. If all strings are single characters, each string will be its own group unless duplicates exist. For instance, Z, B, would result in B, Z. Duplicate strings must always be grouped together, such as in ABC, ABC, XYZ, which outputs ABC, ABC, XYZ. These considerations ensure your solution works for all possible scenarios. To solve this problem, we first considered the brute force approach. This involves comparing every pair of strings to check if one can be shifted to match the other. To do this, we calculate the difference between corresponding characters in the strings, wrapping around with modulo 26 to account for cyclic shifts. If these differences are consistent across the entire string, the strings belong to the same group. However, this method has a significant drawback. The time complexity is O, n squared asterisk m, where n is the number of strings and m is the average string length, making it impractical for large inputs. Additionally, while the space complexity is manageable at O, n, for storing the groups, the inefficiency of comparing every pair of strings makes this approach unsuitable for scaling. Instead, we turn to an optimized approach that uses hashing. Here, the goal is to categorize strings into groups based on a unique key, which represents their shift pattern. This key is calculated by finding the relative differences between consecutive characters, using modulo 26 to handle wraparounds. By storing these keys in a hash map, we can group strings efficiently without performing pairwise comparisons. This reduces the time complexity to O and *m, with space complexity of O and *m, for the hash map and resulting groups. Let's explore why this hashing-based approach is more efficient and how exactly it works. The optimized approach comes with several trade-offs that make it both efficient and practical. By avoiding pairwise comparisons, we eliminate the quadratic time complexity of the brute force method. Hashing allows us to group strings in constant time for insertions and lookups, which significantly improves performance. However, we do require additional space for the hash map. This is a worthwhile trade-off, as the overall complexity remains much more manageable for larger inputs. The strategy we chose centers on this optimized approach because it provides a balance between efficiency and clarity. The key insight here is that the shift pattern of a string is invariant within its group. Any string in the group can be shifted to start with a, and the pattern of differences between characters remains the same. This insight allows us to use hashing effectively to categorize strings. Comparing this to alternatives, we ruled out the brute force approach due to its inefficiency at scale. Instead, hashing provides an elegant way to group strings while reducing redundant work. Although the additional space complexity is a factor, the significant reduction in time complexity makes this approach superior. It's also worth noting that the problem constraints, specifically that strings consist only of lowercase English letters, simplify the modulo operations and make hashing an even more attractive choice. In conclusion, the optimized approach using hashing stands out as the best solution for this problem. It is computationally efficient, scaling well even when the input size grows, and it's relatively straightforward to implement. By leveraging the invariant shift pattern of strings in the same group, we can efficiently group them without redundant comparisons. This approach strikes the right balance between time and space complexity, making it an ideal choice for solving the problem. To solve the problem of grouping shifted strings, we start by understanding the concept of shift equivalence. Two strings are classified as shift equivalent if we can transform one into the other by cyclically shifting each character by the same amount within the alphabet. For instance, the string ABC can be shifted by 3 positions to become def, making them shift equivalent. The goal is to group all such strings that share this property. To approach this, we begin with the input list of strings and initialize an empty dictionary called groups. This dictionary will store the grouped strings, using a unique signature for each group as the key. For example, given the input list, ABC, def, XYZ, BCD, our algorithm will organize these strings based on their shift equivalence into appropriate groups. The next step is to calculate a unique signature for each string, which will act as an identifier for grouping. This signature encodes the relative shifts between consecutive characters in the string. To compute it, we take each pair of consecutive characters and calculate the difference between their positions in the alphabet. This difference is taken modulo 26 to account for the cyclic nature of the alphabet. For example, in the string ABC, the shift from A to B is 1, and the shift from B to C is also 1, resulting in a shift signature of 1, 1. Similarly, for the string XYZ, the shift from X to Y is 1, and from Y to Z is 1, producing the same signature of 1, 1. This signature will help us identify and group strings that are shift equivalent. Using the computed signature, we then group the strings. Each signature serves as a key in the group's dictionary, and strings with the same signature are added to the corresponding list. For instance, the strings ABC, XYZ, BCD, and def all share the signature 1, 1, so they are grouped together under this key. The resulting dictionary will look something like this: it groups 1, 1 equals ABC, XYZ, BCD, def. Once all strings are processed, we extract the values of the dictionary as the final output, which is a list of groups. For our example, the output will be ABC, BCD, XYZ, def, representing all the strings that are shift equivalent grouped together. The algorithm hinges on several key insights. First, the use of shift signatures is crucial because these signatures remain consistent for all strings within the same shift equivalent group. This ensures that we can reliably identify and group strings based on their signatures. Second, this approach is a significant optimization over a brute force method that would compare every pair of strings, which would be computationally expensive. By reducing the problem to computing signatures, we achieve a more efficient n*(m) complexity, where n is the number of strings and m is their average length. Finally, we must handle edge cases carefully. Single character strings, for example, always have an empty signature, so all such strings belong to the same group. Empty strings can be handled by returning an empty group, and we ensure that the input strictly adheres to constraints such as being lowercase alphabetic strings. The data structures used in this algorithm are chosen for efficiency and clarity. The group's dictionary is the central structure, where the keys are tuples representing the shift signatures and the values are lists of strings that share the same signature. This organization allows for efficient grouping and retrieval. Tuples are used for signatures because they are immutable and hashable, making them ideal for use as dictionary keys. These choices ensure that the algorithm remains both performant and easy to implement. Analyzing the algorithm's complexity, the time complexity is primarily determined by the signature computation and grouping processes. Computing the signature for a single string takes m, where m is the string's length. For n strings, this totals n*(m). Grouping each string is an average O(1) operation, so the overall time complexity remains n*(m). In terms of space complexity, the group's dictionary requires storage proportional to the total length of all strings, which is n*(m) in the worst case. This efficient use of time and space ensures the algorithm can handle large inputs effectively. The problem requires us to group strings that are shift equivalent. Two strings are shift equivalent if, for each character in one string, the corresponding character in the other string is shifted by the same number of positions cyclically within the alphabet. The solution starts by defining a helper function get_key, which calculates a unique key for each string based on its shift pattern. The key is computed as a tuple of differences between consecutive characters in the string. These differences are taken modulo 26 to account for cyclic shifts within the alphabet. A defaultdict is used to store lists of strings that share the same shift pattern. For each string in the input list, we calculate its key using the get_key function and append the string to the corresponding group in the defaultdict. Finally, we return the grouped strings as a list of lists, extracted from the values of the defaultdict. This approach ensures that strings with the same shift pattern are grouped together efficiently. The time complexity is n*(m), where n is the number of strings and m is the average length of the strings, because we compute the key in m time for each string. The space complexity is n*(m), to store the groups and the keys. Here, we begin by defining a method called groupStrings inside the solution class. This method takes an array of strings as input and groups them based on their shift patterns. To achieve this, we use a hash map called groups where the keys represent the unique shift patterns, and the values are lists of strings that share the same pattern. For each string in the input array, we generate its shift pattern key using the helper method getKey. This key is a unique identifier for the cyclic differences between consecutive characters in the string. Once we have the key, we use the map's computeIfAbsent method to add the string to the appropriate group, creating a new list if the key doesn't already exist in the map. Finally, we return all the grouped strings as a list of lists using the values method of the map wrapped in a new array list. Now, let's look at the getKey method, which calculates the shift pattern for a string. The getKey method constructs a unique string representation of the shift pattern for a given input string. It uses a string builder to build this pattern by iterating through the string, starting from the second character. For each pair of consecutive characters, it calculates the cyclic difference, ensuring the result is always non-negative by adding 26 before taking the modulo. These differences are then appended to the string builder, separated by commas, to create a unique key for the string. At the end of the loop, the complete pattern is returned as a string. In the main method, we test the solution with an example array of strings. The groupStrings method is called, and the result is printed to the console, showing the grouped strings based on their shift patterns. This demonstrates how the implementation organizes strings with similar shifting characteristics into distinct groups. We start with the input list of strings, ABC, BCD, ASF, XYZ, AZ, BA, Z. First, we initialize a default called groups where each key will map to a list of strings. Initially, groups is empty. Now, we process each string one by one. For the string ABC, we call the helper function get_key. This function calculates the differences between consecutive characters, modulo 26. For ABC, we compute the differences as 1 and 1, giving us the key 1, 1. We then add ABC to the list corresponding to this key in groups, resulting in 1, 1, ABC. Next, we process BCD. The differences between its characters are also 1 and 1, so the key remains 1, 1. We add BCD to the same group, updating groups to 1, 1, ABC, BCD. Now we process the string ASF. Using get_key, we calculate the differences as 2, 2, and 1, which gives us the key 2, 2, 1. We add ASF to its corresponding group, updating groups to 1, 1, ABC, BCD, 2, 2, 1, ASF. Next, for the string XYZ, the differences between characters are 1 and 1, resulting in the key 1, 1. Since this key already exists, we add XYZ to the same group, making groups 1, 1, ABC, BCD, XYZ, 2, 2, 1, SF. Processing AZ, we compute the difference as 25, so the key becomes 25. We add AZ to this new group, updating groups to 1, 1, ABC, BCD, XYZ, 2, 2, 1, SF, 25, AZ. For the string BA, we find the difference between its characters is 25, so the key is also 25. We add BA to the group with this key, updating groups to 1, 1, ABC, BCD, XY, 2, 2, 1, SF, 25, AZ, BA. Next, we process A, which is a single character. In this case, the key is an empty tuple. We add it to the group corresponding to this key, resulting in 1, 1, ABC, BCD, XYZ, 2, 2, 1, SF, 25, AZ, BA. Finally, for the string Z, another single character, the key is also. We add Z to the same group, updating groups to 1, 1, ABC, BCD, XYZ, 2, 2, 1, SF, 25, AZ, BA, Z. After processing all strings, we have our final groups dictionary 1, 1, ABC, BCD, XYZ, 2, 2, 1, SF, 25, AZ, BA, Z. The last step is to convert this dictionary into a list of grouped strings. The resulting output is ABC, BCD, XYZ, SF, AZ, BA, Z. Moving to another example, consider the input, A, B, C. First, we initialize groups as an empty dictionary. Then, for the string A, since it is a single character, the key is. We add it to the group for this key, making groups A. Next, we process B, which also has the key. We add B to the same group, updating groups to A, B. For the string C, as it is a single character, the key remains. We add C to the same group, resulting in A, B, C. Finally, we convert groups into a list of grouped strings, giving us the output, A, B, C. Now, for another example, let's take the input, A, B, C, D, F, G. As usual, we start by initializing groups as an empty dictionary. Processing A, we calculate the difference between its characters as 1, resulting in the key 1. We add A to the group for this key, making groups 1, A. Next, for BC, the difference between its characters is also 1, so the key remains 1. We add BC to the same group, updating groups to 1, A, BC. For DE, the difference is again 1, giving the key 1. We add D to the same group, resulting in 1, A, BC, DE. Finally, for FG, the difference between its characters is 1, so the key is still 1. Adding FG to the group updates groups to 1, A, BC, D, FG. Converting this dictionary to a list of grouped strings gives the output, A, BC, D, FG. To analyze the time complexity of this solution, we start with the outer loop, which iterates through all the strings in the input list. If there are n strings, this loop contributes O, n, to the overall complexity. For each string, we calculate a unique key using the get_key function. This function iterates through the characters of the string to compute the shift pattern. If the length of the string is k, the key calculation takes k time for that string. In the best case, where strings are very short, such as single character strings, this step contributes n in total. However, in the worst case, where all strings are of maximum length k, the cost adds up to n*k. Finally, grouping strings by their keys involves adding each string to the dictionary. Since hashing the key and appending to a list are constant time operations on average, this step contributes another n overall. These steps together give us the basis for the time complexity analysis. Now, combining the contributions from these steps, we find that the total time complexity is n in the best case, where strings are very short, and n*k in the worst case, where all strings are long. Turning to space complexity, we first consider the dictionary used to store the groups. In the worst case, where all strings have unique keys, the dictionary will have n entries, each containing one string. The memory needed for the keys and values is proportional to the size of the input, resulting in n*k in the worst case. Additionally, generating the keys themselves requires space proportional to the length of the strings. Since each key is a tuple derived from a string of length k, this contributes another n*k to the space complexity. Together, these factors shape the storage requirements of the solution. Another aspect of space complexity comes from the temporary list used in the get_key function to store the differences between characters. This list requires k space per string. However, since this space is reused for each string, it does not add to the overall space complexity. Combining all these components, the total space complexity is n plus k in the best case, where strings are short and share many keys, and n*k in the worst case, where all strings are long and have unique keys. When comparing this optimized approach to a brute force method, the difference becomes clear. A naive approach would involve comparing every string with every other string to determine group membership. This would require n²k time in the worst case, significantly higher than the n*k achieved here. While the naive approach avoids extra space for grouping, the optimized solution uses a dictionary to achieve a dramatic reduction in time complexity, with a manageable n*k space overhead. Finally, let's solidify our understanding with a mathematical proof of the big O complexity. The get_key function processes each string by iterating through its k1 characters, making its individual complexity k. Since the outer loop iterates n times and get_key is called once per string, the total time complexity for generating keys and inserting strings into the dictionary becomes n*k. Space usage is also proportional to the size of the input strings and the dictionary, resulting in n*k in the worst case. This efficient design ensures that the solution scales well with both the number of strings and their lengths, making it a significant improvement over the brute force approach when handling large inputs. One of the most common mistakes when solving the group shifted strings problem is ignoring edge cases. Scenarios such as empty strings, single character strings, or strings of varying lengths might seem trivial, but they can easily crash your program if not explicitly accounted for. For example, an empty string might cause an index error, or assuming all inputs are the same length could lead to incorrect results. Another frequent issue is misunderstanding modular arithmetic. Since the problem relies on character shifts within the alphabet, computations often involve modulo 26. Errors here, like failing to handle negative results or wraparounds from z to a, can lead to logic errors that cascade through your solution. Lastly, overusing nested loops is a pitfall in this problem. A brute force approach that compares all pairs of strings is tempting but inefficient. Instead of a time complexity that balloons with larger inputs, you can optimize using hashing techniques, which are significantly faster and more scalable. Another critical oversight is ignoring constraints in the input. For instance, if you assume all strings are lowercase or non-empty but don't verify these assumptions, your solution may behave unpredictably when given unexpected inputs. Always validate constraints to ensure robustness. Additionally, unoptimized hashing logic is a frequent stumbling block. If your approach groups strings using inefficient hashing or fails to handle hash collisions, the performance can degrade significantly. Worse, it may lead to incorrect groupings, which undermines the entire solution. Efficient hashing, combined with proper collision handling, is vital to maintaining both performance and correctness in this problem. When tackling this problem in an interview, there are a few key practices that can make a strong impression. First, demonstrate your awareness of edge cases. Bring up examples like empty strings, single character strings, or strings with repeated characters, and explain how your solution handles them. This shows thoroughness. After presenting a brute force solution, quickly pivot to an optimized approach, such as hashing or pattern recognition, to prove you can refine your ideas. Modular arithmetic is another area to emphasize. Clearly explain how it ensures the alphabet's circular nature, as this demonstrates attention to detail. Be ready to discuss trade-offs, like the space complexity of hash maps versus the time complexity of pairwise comparisons. Lastly, showcasing pattern recognition can set you apart. If you can connect this problem to others, like grouping anagrams or cyclic rotations, it signals a deeper understanding of problem-solving patterns. The group-shifted strings problem is closely related to several others in LeetCode. For example, group anagrams involves clustering words that are anagrams of each other, while valid anagram checks if two strings are anagrams. Problems like rotated digits and longest substring without repeating characters also share themes of analyzing patterns and managing constraints. In terms of alternative approaches, a hashing-based method is highly efficient. By using the differences between characters as a hashable pattern, you can group strings by their shift signatures in O and *k time. However, this approach requires additional space for hash maps. A sorting-based approach is another option, where you sort each string's characters and group them by their sorted version. While easier to implement, it's less optimal for large inputs due to the overhead of sorting. Lastly, a brute force approach compares all pairs of strings to validate shifts. Though straightforward, this method is inefficient, with a time complexity of O and squared *k, making it suitable only for small-scale problems. Another alternative to consider is a mathematical approach. Here, you represent each string as a numerical sequence and analyze transformations mathematically. This method can sometimes uncover unique insights or optimizations, though it's conceptually more complex and may only be efficient in niche cases. While not always the most practical option, understanding this approach can deepen your grasp of the problem's underlying structure and prepare you to adapt its ideas to other challenges. Great job! We've covered the key insights for solving group-shifted strings. Remember to practice similar problems and refine your approach. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!